So for this session, we'll be doing section 2.3, properties of determinants and the Cramer's rule. Okay, so last time we talked about determinants. Particularly, we defined or we discussed several ways on getting determinants of n by n matrices. So we have the row reduction method, we have the cofactor expansion method. And for 2 by 2, we had a formula or method. We discussed that several days ago. And for the 3 by 3, we also had similar methods. But the methods that we have for 2 by 2 and 3 by 3 matrices, they cannot be applied to higher sizes. Okay, so that's why if you have a 4 by 4, 5 by 5, etc. matrices, either you use your row reduction method or you use your cofactor expansion method. Okay, so here let us discuss some properties of determinants. Let's start with the following. So let A be an n by n matrix and let K be a scalar. Okay, then if you multiply your matrix A by the scalar K and you get the determinant of that, then it will be equal to K raised to the n times the determinant of A. Okay, so K raised to n times the determinant of A. So for example, if you have this 4 by 4 matrix and you want to get the determinant, so notice the entries have K as a scalar multiplier. So you have KA11, KA12, KA13, KA14, etc. until KA44. So K is multiplied to the matrix with entries A11, A12, A13, A14 until A44. So this is a 4 by 4 matrix. And using this theorem, the determinant will just be k to the 4 times the determinant of this matrix without those k's. Okay, so this guy here, it's equal to k to the 4 times the determinant of A11, A12, etc. until A44. Okay, and this guy here, this theorem, follows from one of the theorems that we discussed before. So let me just let us look at that. We have this. I guess it's this guy here. So if the matrix B resulted by multiplying a single row or single column of a scalar K, then the determinant of B is equal to K determinant of A. So we have a K here, okay? And this K was multiplied to a single row or a single column, okay? Now for this, when you multiply the scalar K to the matrix A, you are multiplying it to all the columns or all the rows of your matrix, correct? So you have here 4 rows, okay? So you will have K times K times K times K. So you will take out K 4 times. So you will get this K to the 4. Okay? Now, if we have 2 matrices and we add them and we tried to get the determinant of that, it is not always the determinant of A plus the determinant of B. Meaning, if you have 2 matrices A and B, you have A plus B, you get the determinant of A plus B, okay? It's not determinant of A plus determinant of B. Okay? So for example, you let your A to be this matrix. It's just 2 by 2, so the determinant can be obtained easily. You have 1, 0, 1, 1. And then you let your matrix B be equal to this matrix 1, 1, 1, 1. So if you want to find the determinant of um, A, you just have what? This times this minus this times this, correct? So the determinant of A here is equal to 1, okay? So the determinant of A, this is equal to 1. And then the determinant of B, you can apply the same method, okay? You have 1 times 1 minus 1 times 1, so that's equal to 0, okay? But you can see clearly this will have determinant equal to 0 because row 1 is proportional to row 2. In fact, row 1 is exactly row 2. So the determinant will be 0. And therefore, you have determinant of A plus determinant of B. This is equal to 1. Okay? Now, if we look at A plus B, so we add the two matrices, we'll just have 1 plus 1 in here, that's 2. And then 0 plus 1, that's just 1. And then the other two entries, they are both 2. So if we calculate for the determinant of A plus B, so we need to get the determinant of this. This is just 4 minus 2, which is equal to 2. And that's not equal to this. Okay? So you cannot just distribute. You cannot just distribute the determinant over the sum. In fact, you cannot do that. Okay? Now, suppose we have the following. We have matrices A and B and C. They are all n by n matrices. And they only differ in a single row, say the rth row. Okay? So all the entries are the same except for this one single row. Now, assume that the rth row of C, okay, the rth row of C can be obtained by adding the entries of the rth rows of A and rth rows of B, or rth row of A and rth row of B. Okay? So all the entries are the same except for the rth row, but the entries in the rth row of C, it's just rth row of A plus rth row of B. Then we have the following. Okay? The determinant of C, it is equal to the determinant of A plus the determinant of B. Okay? And the same result holds for columns. So instead of row here, you replace it by column. So how is this? Let us look at this particular example to understand the theorem. So this is your C. Okay, this is your C. You have 2, 1, negative 4, negative 5, 2, 6, and then here you actually have 1, 5, 4. Okay, so let me write that as 1, 5, 4. But on the third row, I decomposed it into 1 plus 0, 2 plus 3, 6 minus 2. Okay? So according to this, the determinant here can be obtained by adding the two determinants, where first row and second row, they are all the same. The third row is just the addends that we see in here. So for the first one, we have 1, 2, 6. That's your 1 here, 2 here, and 6 in here. And then for the second matrix here, you have 0, 3, negative 2. So 0, 3, negative 2. Okay? So again, first row and second row, they are all the same. The third row, they are different. Okay? But as you can see, on the left-hand side, the decomposed third row is 1 plus 0, 2 plus 3, 6 minus 2. And then on the right-hand side, we get the first addends on this matrix. We put it on the third row of this matrix. And then we get the second addends on this matrix. We put it on the second matrix here. So I leave this to you to verify that the determinant of this is equal to the determinant of this plus the determinant of this. And you can use any method that we learned last time. Okay? Questions so far? Now, we don't have a distribution of this determinant operator over the sum. Okay? We don't have this guy here. Okay, meaning the determinant of a plus b is not equal to the determinant of a plus the determinant of b. However, we can somehow distribute the determinants over products of matrices. Okay, so let us start with the following. Let B be an n by n matrix, and let E be an n by n elementary matrix. So E is an elementary matrix. Okay, and the elementary matrix is obtained by doing a single row, elementary row operation on the identity matrix. You either have the identity matrix and then you apply switching of rows, it's one, or you multiply a row by some scalar k, that's another, or you add a row, you add a multiple of row to another row, that's the third one. Okay, then you multiply the matrices E and B. Okay, and then you get the determinant of EB. That will be equal to the determinant of E times the determinant of B. Okay, so again, you have an n by n matrix B. You have an elementary matrix E, an n by n elementary matrix E. You get the product EB. Then the determinant of that product EB, it's equal to the determinant of E times the determinant of B. Okay? Now, coming from this theorem, it can be done or it can be proved that a square matrix A is invertible if and only if the determinant of A is not equal to 0. Okay? So a square matrix A is invertible if and only if the determinant of A is not equal to 0. And the proof of this will be easy once you know this fact here. A is invertible, it means A inverse exists. Okay? A inverse exists. And then what? You can multiply A times A inverse, that's equal to I. Okay? And the determinant of I, that's just 1. And later, you can find that since A is, actually you start with A, you multiply elementary matrices to A to obtain I. Okay? To obtain I. And then you use this. You use this fact to show that the determinant of A will not be equal to 0. Yeah, let us try that one. So proof. Okay. So on that direction, okay, we are proving that direction, meaning we assume A is invertible. So suppose A is invertible, okay, then there exists elementary matrices. There exists elementary matrices, elementary matrices. Let's write E1, E2 until EK, such that when you multiply these elementary matrices, okay, to the matrix A, you will get I. Okay? So, you will have, you get the determinant of this guy here, okay? You have determinant of EK, etc., until determinant of E2, determinant of E1, and then you have your A here. This is equal to the determinant of your I, but the determinant of I, it's just 1. Okay? So by by the lemma, by the lemma above, okay, you can distribute, meaning you will have determinant of EK times until you have determinant of E2, determinant of E1, determinant of A. And this is equal to 1. Okay? Therefore, the determinant of A cannot be 0. Because if determinant of A equals 0, then this product here must be equal to 0, which is a contradiction. Okay? Therefore, let me just write it here. Therefore, determinant of A cannot be 0. Okay? So that's the forward direction. We assume A is invertible. Okay? And then we prove that the determinant of A equals 0. Now, I want you to show the other direction as an exercise. You assume determinant of A not equal to 0. Okay? So let me add that. So proof of the other direction. Okay, this will be exercise. So in here, assume determinant of A not equal to 0. Show that A is invertible. Show that A is invertible. Okay? So that's an exercise. Could be 3 or 4 sentences also. Okay? But this will be straightforward. Okay? Now, also, following from this, okay, we have the following theorem. If A and B are n by n matrices, then the determinant of AB, it is equal to the determinant of A times determinant of B. So in here, you have a matrix B and an elementary matrix. Okay? In here, you can have any matrix as long as they are square and of the same size. So the determinant of AB, it's equal to the determinant of A times the determinant of B. Okay? Let's do that here. Let's find the determinant of A. So in here, your matrix A, it's 3, negative 1, 1, 1. So this will be 3 times 1 minus 1 times negative 1. So this is equal to 4. And then we get the determinant of B. You have 1 times 6 in here. 1 times 6 minus 5 times negative 2. And this is equal to 16. Okay? So in here, on the left-hand side, we need the product AB. So let us multiply AB. So we have 3 times 1, that's 3, plus negative 1 times negative 2, that's positive 2. And then 3 times 5, that's 15, plus negative 1 times 6, that's minus 6. Then 1 times 1, that's 1, plus 1 times negative 2, that's minus 2 there. And then 1 times 5, that's 5, plus 1 times 6, that's 6. So if we simplify this, we will have 5, 9, negative 1, 11. So this is the product AB. And then the determinant of the product AB, this is equal to 5 times 11 minus 9 times negative 1. So we have 55 plus 9, and this is equal to 64. And indeed, that's 4 times 16. Correct? Determinant of A times determinant of B, this is equal to 4 times 16, this is equal to 64. So they are equal. So at least using these matrices, we have confirmed the identity. But it is always true. Okay? It is always true. You have matrices, you have n by n matrices A and B, you multiply them, you get the determinant, it's equal to the product of their determinants. Okay? Question. And now, from this theorem, okay, from this theorem, we can prove that the determinant of A inverse, it's just the inverse of the determinant. Okay? So, if A is invertible, then A inverse exists. Furthermore, the determinant of A inverse, that's equal to 1 over determinant of A. So to prove this, we have the following. A inverse A. This is, well, we want to get the determinant of this. Okay? But A inverse A, that's equal to the I. So we need to get the determinant of I. Okay? And then using the previous theorem, we will have determinant of A inverse times the determinant of A. Therefore, so determinant of I it's 1, since determinant of I, this is equal to 1, it follows that the determinant of A inverse, this is equal to 1 over determinant of A. Okay? Questions? Now, let us remember your minor and cofactor of entries. So, let A be an n by n matrix, and let Cij be the cofactor of the entry Aij. So remember that. You have the minor Mij, then the cofactor Cij, this is equal to negative 1 raised to I plus j times Mij. Okay? So if we collect all of these Cij, we can form the matrix. Okay? And this is called the matrix of cofactors from A. So C11, it's the cofactor of the entry A11 of A. C12, cofactor of the entry A12 of A, etc. So you collect all of them, you put them into a matrix. So create a matrix with entries, the cofactor. So you have a matrix of cofactors. Now, if you get the transpose of this, okay, it will be the matrix called adjoint of A. It is denoted by this symbol here. Okay? So in our course, we use the word adjoint. Okay? In some other references, you might see the matrix here to be the adjugate, okay, or called adjugate. So the transpose of this matrix is called adjugate of the matrix A in other references. But for us, we will call it adjoint of A. Okay? So take note, you need the cofactors. And to get the cofactors, you need the minor. Okay? So, any questions so far? Now, let us find the adjoint of this matrix here. Okay? So, let's start with M11. So, M11, you have the entry here. Okay? You have the entry here. So, I hope you remember that. You have the entry here. To get M11, you cover this and you cover this and get the determinant. Okay, get the determinant of the submatrix. Okay, left after deleting those row and column. So this is just the determinant of the matrix 2626, and you will clearly see that this is just equal to 0. Let's have M12. This is the entry 1, 2. So you cover this row, you cover this column, and then the determinant will be, or the minor will be the determinant of the matrix negative 5, 6, 1, 6. So if we do this, we will have negative 30 minus 6. This is equal to negative 36. And then let's have M13. So this time, we cover, or we get this entry here, then we cover this and we cover this. So M13, it's the determinant of the matrix -5 here, 2 here, 1 and 2. So if we calculate, we will have -10 minus 2. This is equal to -12. And then while I'm writing all the other minors, please work on your desk and continue finding the minors of other entries. So for this entry here, we have minor or so M21. Okay. So we delete this part here and then this part here. We'll have 1, -4, 2, 6. So this is equal to 6 minus -8. So this is 14. Let's have M22. So this is the 2 entry. Delete this and this. We have determinant of 2, -4, 1, 6. This is 12 minus -4. This is positive 16. And then M23. This is the 2, 3 entry. We delete this and we delete this. So M23, it's the determinant of this matrix, 2, 1, 1, 2. And this is equal to 4 minus 1, which is equal to 3. And then last 3 entries here, we have M31. You have the determinant of 2, 1, 1, 2. Sorry, it's M31. Determinant of 1, -4, 2, 6. So this guy here, this and this. We have 1, -4, 2, 6. This is equal to 6 minus -8, and this is equal to 14. M32, we have this guy here, delete and delete, and we'll have 2, -4, -5, 6. So this is 12 minus 20. This is equal to -8. Then finally, we have the M33. We have 2, 1, -5, 2. So this is equal to 4 minus -5, and this is equal to 9. So these are the minors. So for the M33, we have this, delete this, and delete this. So you have 2, 1, -5, 2. Okay? And then we can now write the cofactor. Okay? The cofactors. So let us have the cofactor matrix here. Cofactor matrix. So for C11, so we need the following. Cij, this is equal to -1 raised to I plus j m ij. So for C11, you have 0. For C12, okay, you have negative of -36. 1, 2, that's 1 plus 2, that's 3. So -1 raised to 3, that's negative. And then this is your M12. So this is positive 36. M13, this is -12. It's still negative 12 because 1 plus 3, that's 4. Negative 1 raised to 4, that's positive 1. M21 here, you have negative 14. M22, you have 16. M23, you have negative 3. M31, you have 14. M32, you have 8. Then M33, you have 9. Okay? So this is the cofactor matrix. Let me label this as capital C. Therefore, the adjoint of A, the adjoint of this matrix, let me label this as matrix A. So the adjoint of A, this is equal to the transpose of C here. So the adjoint is just 0, 36 here, and negative 12 here. You have negative 14, 16, and negative 3. And then we have 14, 8, 9. So this is the adjoint of this matrix A in here. Okay? Okay. Now, in relation to the adjoint, okay, we can find the inverse of a matrix if it is invertible. So if A is invertible, then A inverse, it is equal to the adjoint of A multiplied by 1 over determinant of A. Okay? So here we have the matrix 2, 1, negative 4, negative 5, 2, 6, and 1, 2, 6. This guy here, it's the same matrix as in this. 2, 1, negative 4, negative 5, 2, 6, and then 1, 2, 6. So to find the inverse, okay, we can use the inversion algorithm if you want, okay, or we can use this. So for this example, we will use this because we already know the adjoint of A. Okay, so I labeled this as A from before. The adjoint of A, it's given by this guy here. Okay, so all we need to do now is to find the determinant and then divide all the entries of the adjoint of A by the determinant. And that will be the inverse of A. So what's the determinant of A now? So we use the method that we learned. The method that we learned, which is similar to the 2 by 2. Okay. So we have 2, 1, 4, negative 5, 2, 6, 1, 2, 6. And then we augment here the first two columns. 2, negative 5, 1, 1, 2, 2. And then we can look at the products of this, and then this, and then this, and then add all of them. So let's start with these guys here. 2 times 2, that's 4 times 6, that's 24. Then 1 times 6 times 1, that's 6. 4 times negative 5, that's negative 20, times 2, that's negative 40. And then we get the products here, here, and here. So we have 1 times 2 times 4. Yes, you are correct. That should be negative 4 there. Thank you. So this is negative 4. So before we proceed, we will have negative 4 times negative 5. That's 20. And then times 2. So this becomes positive 40. Thank you for that. And then for the going up, we have 1 times 2 times negative 4. that's negative 8. Then 2 times 6 times 2, that's 24. 6 times negative 5 times 1, um, that's negative 30. Okay? Therefore, determinant of A, this is equal to 24 plus 6 plus 40 minus quantity. You have minus 8 plus 24 minus 30. Okay? So if we simplify this, we have here 24 plus 6, that's 30, plus 40, that's 70, minus in here, I have 24 minus 30, that's minus 6, and then minus 8, that's minus 14, so plus 14. So this is equal to 84. Okay? Therefore, adjoint or the inverse of A, that's 1 over 84 times the matrix from this slide in here. Okay? So I'll just copy this. And then paste it here. Okay? And then we'll just multiply this 1 over 84 to each entry that we see in here. And that will be the inverse. Okay? So just write out the entries here. Questions? So of course, if you don't know the adjoint and you are asked to find the inverse, just use inversion algorithm. Okay? Just use the inversion algorithm and you will easily find the inverse using the inversion algorithm. However, if you already know the adjoint, okay? If you already know the adjoint and you are asked to find the inverse, this will be faster. Okay? Because the next job that you need to do is just to find the determinant of A. And then you get the reciprocal of that, you multiply that to the given adjoint. You have the inverse. Okay? So just write this out. Just write everything here. And from the 6 statements that we had from before, we can now add the last statement here. Remember that if you have a matrix A, which is n by n, then A is invertible if and only if the determinant of A is not equal to 0. So this statement here, it's equivalent to this statement A, and therefore they are all equivalent. All of them should be true or all of them should be false. No one is left behind. Okay? Questions? Now, we go back to finding solutions to linear systems. Okay? So we had the Gauss-Jordan method to solve a linear system. Okay? And we can either work on the augmented matrix and find the RREF of that to find the solution, or just straight from the set of equations that we that you have. There's another way of finding solutions of a linear system, and that's called the Cramer's rule. Okay, but this has a certain restriction. Okay, so if you have a matrix A, okay, which is n by n, and you consider the linear system AX equals B, and of course, with that, you have n unknowns. Okay? So AX equals B will have n unknowns and n equations. So suppose you have that system, and suppose that the determinant of A is not equal to 0. Okay? Then the system has a unique solution. And we know that. We know that from this theorem here. There is exactly one solution. Okay? But the Cramer's rule added the following. The solution can be obtained using this. You have x sub 1, the first variable will just be the determinant of A1 over determinant of A. X sub 2 will be the determinant of A2 over determinant of A, etc. Until x sub n, you have determinant of A sub n over determinant of A. But what are these A sub 1, A sub 2, A sub n? So they are the matrix. For example, you look at the matrix A sub j. It is the matrix obtained by replacing the jth column of A by the entries in the matrix B. Take note that B here, it's just a single column. So you get the column J, remove that, and replace that with this matrix B. That will be your AJ. So it's still an n by n matrix. So you can get the determinant of that. And notice here, this only works if the determinant of A is not equal to 0. You see the determinant of A, or it is on the denominator of each of these variables here or solutions here. So the determinant of A cannot be 0. If the determinant of A is equal to 0, you cannot use this. Okay? Let's try this Cramer's rule. So you have this. Use Cramer's rule to solve the system. In here, your matrix A, this is equal to 1, -4, 1. That's for your first equation. For the second equation, you have 4, -1, 2. For the third equation, you have 2, 2, -3. This is your this is your matrix A. Your matrix B, it's just the constant part. You have 6, -1, -20. Okay? Now, determinant of A. So again, we use the same method as in just the last time. We have 1, -4, 1, 4, -1, 2, 2, 2, -3. And then you augment the first two columns, 1, 4, 2, -4, -1, 2. Then you do this. And this guy here, and then this guy here. So we have +3 in here. And then we have -16 in here. Then we have +8 here. For the going up, this guy here, this guy here, and then this guy here. So you have 2, -1, 1, that's -2. 2, 2, 1, that's 4. -3, 4, -4. This is 48. So the determinant of A, it's 3 minus 16 plus 8 minus quantity -2 plus 4 plus 48. So if we simplify this, what do we get? we have negative 5 minus, in here we have 50. So this is equal to negative 55. Okay? And then, this is the determinant of A. Let us solve for A sub 1. Since I'm using variables x, y, z, not x sub 1, x sub 2, or x sub 3, I'll put the subscript of using the variables x, y, z. So for example, now I will have A sub x. So the A sub x, we will replace the column for x by the matrix B here. So here we will now have 6, negative 1, negative 20. And then you just copy the other two columns here. Negative 4, negative 1, 2. Then 1, 2, negative 3. And then you find the determinant of this. Okay? So here, determinant of A sub x. Let's try to do this again. This method again. So I have 6, negative 1, negative 20. Then negative 4, negative 1, 2. 1, 2, negative 3. Augment the first two columns, negative 6, negative 1, negative 20. Negative 4, negative 1, 2. Then you calculate. Okay? You calculate this. We will have 6 times 3, that's 18. Negative 4 times 2, that's 8 or negative 8 times negative 20, that's 160. Then 1 times negative 1 times 2, that's negative 2. And then for the going up, this guy there, or this here, or this here, we have negative 20, or it's positive 20. And then we have 24 in here, and then we have 12 in here. So the determinant of A sub x, that's 18 plus 160 minus 2 minus quantity 20 plus 24 plus 12. So if we simplify this, we will have 176 minus 56. So this is equal to 120. Okay? Therefore, Cramer's rule says that your x, this is equal to the determinant of that matrix A sub x over the determinant of A, and this is just 120 over 55. So this is the value of x that will solve the system. Okay? And take note that I didn't have to solve for y and z. Okay? But of course, we want the solution to the system, so we need to solve for y and z also. So let's just continue. Let's find y and also z. Oh, by the way, determinant of A, it's negative 55. So there should be negative in here. Okay? Now let's do A sub y. So A sub y, this is the matrix. So you copy the column for x and column for z. The column for y, you will replace it by this constant column. So we have here 1, 4, 2, and then 6, negative 1, negative 20, and then 1, 2, negative 3. So we want the determinant A sub y. So we have here 1, 4, 2, 6, negative 1, negative 20, 1, 2, negative 3. Then we augment 1, 4, 2, 6, negative 1, negative 20. So we do the multiplication now. And this will be positive 3 here. And then 6 times 2 times 2, that's 24. 1 times 4 times negative 20, that's minus 80. And then for this guy here and this guy here, we have negative 2, negative 40, and then negative 72, which means that determinant of A sub y, this is equal to 3 plus 24 minus 80 minus negative 2 minus 40 minus 72. So this is equal to what? For this guy here, we have 27 minus 80. That's 53 or negative 53. And then for the other guy, we'll have plus. So we have here y plus because these are all negative and you have a negative here. So I'll just add them. 2 plus 40, that's 42 plus 72, that's 114. Correct? 114. And this is equal to 60 or 71 or 61. I think it's 61. Okay? And which means that y, this is equal to the determinant of A sub y over determinant of A. And this will be 61 over negative 55. Negative 55, the determinant of A. Okay? And then finally, which I will leave to you, the complete solution. So you will have your A sub z. So this time, you will replace the z column by this column here. So A sub z, it's just 1, 4, 2, negative 4, negative 1, 2. And then 6, negative 1, negative 20. And then find the determinant of this. Okay? So find that of A sub z. And then you will have z equals that A sub z divided by determinant of A. So you have your x, you have your y, and you have your z. You now solved the system. Okay? Now, what's good thing about this Cramer's rule? If you are only asked to find the value of one quantity to solve that solves the system, then Cramer's rule is really helpful because, well, you can just compute for x sub 2 without knowing x sub 1 until x sub n. Or you can just compute x sub n without knowing x sub 1 until x sub n minus 1. So this one is a nice help if you are only interested in solving one of the variables. Okay?